Welcome to the session on algebraic methods, repeated factors. The objectives for this session are to convert an expression with repeated linear factors in the denominator into partial fractions. A single fraction which has a repeated linear factor in the denominator can be split into two or more separate fractions. So, for example, we have this equation here, or this identity. The denominator on the left-hand side contains three linear factors, namely x plus 7, x plus 5, and x plus 5. Here, of course, x plus 5 is repeated. On the right-hand side, we have a, b, and c, which are constants which can be found. The expression on the left has been rewritten as the sum of three partial fractions. Notice that x plus 7, x plus 5, and x plus 5 all squared are the denominators. Let's now take a look at an example. We are required to split the fraction shown into partial fractions. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We're going to begin by letting this fraction be identical to a over x plus 3 plus b over x plus 4 plus c over x plus 4 all squared. For some constants a, b, and c. Adding these three partial fractions together and putting them over one common denominator gives us this expression here. Now, since the denominators are the same, as you can see highlighted in red, we can conclude that the numerators are the same. When x equals minus 4, this is going to allow us to calculate the value of c, because the a term and the b term will disappear. On the left-hand side, we have 2 times 16 plus 19 times minus 4 plus 42 when we plug in x equals minus 4. This is equal to minus 2. And on the right-hand side, when we plug in x equals minus 4, as intended, the a term and the b term will disappear because we're going to multiply each of them by 0. This is what we intended to do, and we're now simply left with c times minus 1. Therefore, the right-hand side is equal to minus c. Since the left-hand side and the right-hand side are equal, we have that c equals 2. When x equals minus 3, on the left-hand side, we have 2 times 9 plus 19 times minus 3 plus 42. And this is equal to 3. And when we plug in x equals minus 3 on the right-hand side, we manage to get rid of the b term and the c term, and this is what we intended to do so that we can find the value of a. So on the right-hand side, we are left with a. Since the left-hand side and the right-hand side are equal, we have that a is equal to 3. So now we have the value of a and the value of c. We only now need to find the value of b. Let's plug in x equal to 0 to simplify our calculations on the left and right-hand side, and also of course plug in a and c in order to find the value of b. So plugging all these in, we have the left-hand side. Of course the left-hand side doesn't have a, b or c, but we can plug in of course x equal to 0. So when we plug in x equals 0, we obtain 2 times 0 plus 19 times 0 plus 42. Giving us that the left-hand side equals 42. When x equals 0, then on the right-hand side we can plug in a equals 3, c equals 2, and x equals 0 to give us 3 times 16 plus b times 3 times 4 plus 2 times 3. Which once tidied up is equal to 12b plus 54. And so, since the left-hand side and the right-hand side are equal, we have that 12b plus 54 equals 42. Giving us that b is equal to -1. We can now plug in the values of a, b and c into our original identity. So c equals 2 goes here as shown, a equals 3 goes here as shown, and b equals -1 here. We now have our original fraction expressed as partial fractions. This brings us to the end of this session. If you have understood its contents, you should be able to convert an expression with repeated linear factors in the denominator into partial fractions. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.